is due Friday. And also you have a bonus assignment that's also due, a bonus R assignment. Now if you look up here, you're going to get these 5 bonus R assignments. These are separate from these R lessons that are the independent study lessons posted here for you to look at. All the homework is here. It's just like what people are getting for credit, but if you just want to look at it, you won't get credit unless you sign up for $3.90. But if you just want to see, just do a few of these assignments, you're welcome to do it. But these are easier, and I recommend you trying them, but you don't have to, as I said. So just if you want to. So that's what's due. These are both due Friday, this and the survey. Of course, you should do the survey. That takes you just 2 minutes, and it'll be fun because we'll analyze it. We'll have our own data to look at. Okay, so now also I just want to show you one other thing, the homework that's due today. We're covering that in class, and so you'll be able to do the homework. If you bring your laptop often, you can do it as we go along in lecture. So, all right, so let's start. And now let's go to the document camera and go to the lecture that's for today. All right, so I think we're on chapter 17, which is our second chapter on multiple regression. We looked at what the slopes in the multiple regression model did last time, and now we're going to look at them more graphically. So as you know, last time we were working on this problem on predicting final exam scores from students. This equation right here, your final exam score, we got this regression equation is equal to 0.1641 times students' homework plus 0.5824 times their exam average plus 11.91. This was based on 107 students from a former Stat 100 class. So as we saw last time, we saw that these slopes in the multiple, like this one and this one, those slopes are not the same that you get if you just look at homework predicting finals alone and exams predicting final alone. We did that right here. For example, here was homework predicting finals. And we saw how they relate, how in the simple regression, that this slope right here was bigger than in the multiple regression, because we saw that in the multiple regression, this slope only, this is the part of this that it predicts final after we've subtracted out the effect of exams. Remember that homework and exams, the picture was that homework positively predicts finals, is positively correlated with finals. People's homework score is a predictor of their finals. An even bigger predictor of their finals was exams, but they were correlated with each other, so we can think of them as overlapping here. And we said that this overlap right here, this part right here, we don't want to double count that. So when we put both of these together, when we put both of them together here and here, in the multiple, that these slopes are going to be smaller because we're going to subtract out the part. For example, when we add homework in, we're going to subtract out the part of the homework that's already been explained by the exams. And you can see how we arrived at this. Look at this. So this slope is smaller than that, and you can see how it's this piece plus that would be our total. And since everything is positively correlated, we know that the multiple regression slopes are going to be smaller than their respective. The other one was, I think it was final equals something times exams plus an intercept. And that is going to be bigger than 0.5824. It was 0.6647. Right? Okay. That's because everything's positively correlated here. Can you see how if it was negatively correlated, we wouldn't necessarily be able to do that if some of these were negative? It would be hard to tell depending on how the signs worked out. But with them all positive, obviously they have to be less than than these two. And if they're uncorrelated, if there's no overlap, they're going to be exactly the same. So when we combine homework and exams into a multiple regression, these two slopes wouldn't change. Does that make sense? Okay. Now, so now we're going to look at Okay, so we're going to look graphically at what these slopes look like here. All right, so we're thinking about it this way. We have observational data. The high and low homework groups are not balanced. People who have high scores on their homework also have high scores on their exams. So it's hard to separate those two out. And the way that those with higher homework also have higher exam scores. And the higher final exams are partially predicted by the higher homework scores and partially predicted by the higher exam scores. So we call the slopes in the multiple regression partial slopes, since they quantify the effect of each variable after the other one is partialed out or controlled for. In other words, these slopes, like this slope right here, describe the effect of homework for people, like this equation for people with the same exams. And here's people, let's do an example. For those with exams equal to 90, so if I put a 90 in there, then the final is equal to 0.164 plus, and then you'll get this intercept here. So it'll be 90 times 0.5824 plus 11.91. So let's do that. So it would be equal to 0.5824 times 90 plus 11.91. And that line right there, so you get an equation with this slope and an intercept, just to add that together, 64.326. So that's for everybody who has the same exam of 90. Now, if you look at people who have an exam of 80, they're going to have the same slope. You see, all these slopes are the same for homework. Homework has the same effect. Multiple regression forces each one of, for every level of the other variable, it forces the same slope, but then we get different intercepts here. We have different equations. So this one would be the same, 0.5824 times 80 plus 11.91. So that's a difference, a drop of what? 10. 90 to 80 is a drop of 10 times 0.5824. So this one will just be 5.824 less. So this right here is, subtract 5.824 off of that, and we get plus 58.502. And this last one is, of course, so we get a different intercept, all with the same slope. Okay? So So the three multiple regression equations over here are those with different exam scores, but all of them say that the effect of homework's the same. That might or might not be true, but that's what multiple regression does. It forces the same slopes here. All right, and so now when we look here at this simple overall regression indicated by this slope, so this would be your simple regression, homework, predicting finals. Okay, this equation right here gave a bigger slope, right? From the previous page, it was final equals 3436. Okay, so that's the simple overall. That's your simple overall regression equation. This one, in this case, is bigger than these that all indicate these are your multiple regression ones. Where the slope is what? It's much smaller for homework. It's 0.1641. And why? Well, because it's separating out the effect of these exams. You see, look at this. The simple, if you don't factor in the exams, then you can't tell what part. The people with the higher homeworks also have these higher exams. People with lower homeworks also have these lower exams. So some of the effect you see here, some of this effect, the effect of, if we were talking about causation, is it homework that causes higher homework scores? Do they really cause you to do better in the final? Well, that would be a confounded effect with exams, because you can't separate out in the simple overall regression, you can't separate out the effect that the homework's having from the effect that homework might just be a marker for people with higher exams, or a huge amount of it could be a marker for people with higher exams. Do you see what I mean? So what the whole point of this is that the simple regression equation estimates finals y from x, ignoring all the other variables, ignoring it all. So you can't tell how much exam scores account for the increased finals and how much homework scores do. That's why when we including that variable, exams, it has the effect of breaking the population into subgroups so that we can compare more balanced groups. Here, everybody has high exams. Here, everybody has middle exams. And here, everybody has low. So then we can see, okay, they all have low. What's the effect of a little bit of a higher exam? Homework. What's the effect? See? Does that make sense to everybody? We did this with binary variables. Now, of course, I just broke it into 3 categories, but you could break it into many, many, many categories. So that's the idea. It's just, as we said before, multiple regression is a way to stratify into like groups, like compare everybody with the same exam scores, by modeling instead of by splitting the graph up. Okay? So we can do the same thing by predicting the effect of exams. Splitting up, looking at this for different levels of the homework, looking at the slope for exams. So basically, all the predictor variables in the regression equation are interpreted controlling for the effects of the other predictor variables, keeping them constant. So the exam slope here, this, describes the effect of exams on finals for those with the same what? Same homework scores. And for those with the same homework scores, this slope tells you that the predicted final score is 0.5824 points higher for each additional each additional exam score, each additional point for a 1-point increase in exam averages. So that's, on the average, how much do people's finals increase for each additional point they gain in their midterms? And the answer is, on the average, it's that. That's what that slope means. Okay, but it's for people with the same homework. For people with the same homework. All right, so we can just simplify this for different homeworks, right? So we look at this equation, and if we put in different homeworks, well, first of all, here's our slope, 0.5824. It doesn't change. And then how does it change for different homeworks? Well, that's going to change the intercept here. So we'll put a 70 in for homework here, and we get 0.1641 times 70 plus 11.91. And I got that to be 23.397. And here you'll do the same thing, but 80. So it increases it by about 1.641 points. And we get 25.038, and then we'll do the last one. This is for 90. So again, we have parallel lines here. So that's 26.679. Any questions on that? Okay. Now, how about, let's look at this problem. Here you had one very similar to this in your homework, and it says the equation for the simple regression, this is final equals 18.51 plus 0.6647 times the exams. Why is this exam slope smaller in the multiple regression? Why is the exam slope smaller in the multiple regression up here? In the multiple regression, it was smaller. It was that. Than in the simple. Well, we just answered that. So which one would be best? Just answer. Pretend you're on an exam question and just circle what you think is right. So did everybody circle 2 here? Nod if you did. Okay, good. Looks like everybody did. And here, no correlation would mean that the two slopes would remain unchanged. Whatever you had in the simple would be the same as in the multiple. And because there's a negative correlation, no. If there was a negative correlation, no, that's wrong. Remember, we just did that. Any questions on this? Okay, so let's move to the next thing. So here's we're on the next chapter, which is chapter 17, and we're going to look at interactions. Now, we already saw in part 4 how an interaction allows for non-parallel slopes. Now we're going to do the same thing here. So we had all these parallel slopes, but how did we know that we should have parallel slopes? In other words, how did when multiple regression forces, without an interaction term, forces all the slopes to be parallel, all the lines to be parallel. But that might not be true. What that's saying is that an improved homework score would make just as much difference for people with low exams as for people with high exams in terms of predicting the final, but that might not be true. Okay? So that's what multiple regression assumes, that each predictor matters the same amount regardless of what values the other predictors have. But sometimes that's not accurate. Often the effect of a predictor variable changes as the value of another predictor variable changes. For example, doing the homework might make more of a difference for people with low exam scores than people with high, or vice versa. So if it's like that, we have to include an interaction term, which would be a multiplicative effect of homework times exams. So here's the basic picture, and this is just what we did before, but the idea is this, that so here's people with, like, these are the people with, all right, right here is the simple overall regression, this one right here. But then if we include another variable for, let's say, high and low exams, well, then it would allow us to go here for high exams, or here, predict for people who have high exams or people who have low exams. So this would be the multiple regression. You see, right now it's just homework predicting finals, and a simple regression is not going to include an exam variable. But if we included an exam variable, like let's say we just had high and low, a binary one, well, then it would split it into, it would be like stratifying into people who have low exams, and this would be their equation and for homework predicting final. And there's no interaction here. If it really looked like this, because the slopes are the same, no interaction. And also no confounding. It doesn't look like there's any correlation between people who have, between homework and exam scores. Okay, but let's say you have correlated predictors. So the people who have the low exams homework down here also have these low exam scores, and the people who have the high homework have higher exam scores. So that would be correlated predictors, and if this is the situation we're in. And so now we have a simple regression that combines those two effects and then inflates the effect of homework on finals. And if we were talking about causation here, it would confound. We would say it would confound. It would be exams would be a confounder. You can't tell, if you just look at the simple regression, you can't tell how much of the effect, how much of this effect of homework on finals is due to the homework. We can once we break it down, and how much is due to the confounded effect of the correlation between the homework and the exams. So this is your multiple, and this is your multiple, right? And in both these cases, the multiple would look like what? The simple regression in both of these would be, the simple regression would be, in all of these, the simple regression would be what? The simple regression equation is of the form finals is equal to some intercept is equal to some slope times your homework plus an intercept, right? Isn't it? I mean, we just have homework and finals, and simple means you just have one variable. Now, in your multiple regression, these two multiple regressions have no interaction term. Why do they have no interaction term? They have the same slopes here. So these two, all these multiple regression, for these, both of them, the multiple regression equation is of the form of what? Final is equal to a slope times homework plus another slope times exams, and that's it, right? Plus an intercept. But no interaction term. There's nothing that allows these slopes to change depending, or this to change depending on the exams. But now we have an interaction effect. We have different slopes. So these are multiple, so the multiple regression is going to include an interaction term. And the simple one would look like what? There's no confounding here. It doesn't look like there's confounding, but there is an interaction term. So that would be your simple, and this would be your multiple regression and multiple. And this one would be of a different, if we wanted to get these predictions, then our multiple regression would look a little bit different. It would look like this, final equals, you'd have a slope times your homework plus a different slope times your exams, plus you'd have to have another slope. These are all different, 1, 2, and 3. A different slope times this interaction term that would allow for different slopes. And then you have an intercept. So you'd have to have 1, 2, 3 slopes. Whereas here you only have 2. Slope 1 and slope 2. Does that make sense? I don't know. I don't want to get too confused here with this picture. Okay, so let's move on. And that was chapter 17. That's done. Read the summaries for all of these. And now what are we going to do here? Okay, so now let's picture all this in 3D and put this all together. All right. So these little dots are the 107 points. Each point represents one person's 3 scores. You have a homework score along here, an exam score along here, and a final score on the vertical axis up here. Does this look right? Let me see what this looks like. From my angle, it's all distorted. I guess it's okay. All right. Now, so you can think of it this way. Given people's homework and exam scores, so some point with just your homework and your exam, you're some point on this plane down here on the homework exam plane, right? Boy, this person didn't get very far off that plane. That's their actual final, just a bare little distance off. Terrible. This person had what? A 65 on the homework, about a 71 or 2 on his exams. And what did he get? He got a 40. I guess it starts at 40. Got a 40. Looks like he just didn't even barely get off that plane. Just a smidgen, maybe a 42. Oh, here he is. This shows how far off he got from that plane. So he got maybe a 42 or something. Terrible score. All right. Whereas this one, look how far off he got from the plane. He didn't do very well either on his homework. He did terrible. 43. But here, what is he at? He had an 80 on the exams. Okay. But then average. But then he got way up here. High. Good, an A. So that's how you can read this. And this multiple regression equation, by the way, I did this in R, these pictures. So if you feel like playing around with R, just do the bonus assignments, and you can, if you're not in the independent R class, and you can see how we make plots and do different things in R. Okay, so here's your multiple regression equation. And now, remember how with just one slope, that's an equation for a line, y equals mx plus b, but now we have 2 slopes. We have an equation, we're predicting y from two variables. So now we have, that describes what? It doesn't describe a line, it describes a plane now. So it's the best fitting plane through all the y's so as to minimize the squared errors above or below the regression plane. And that's what this does. That's what this is. That's how we arrive at these slopes. To minimize the sum of the square distances, our prediction errors from an actual, like this person, we have a big positive residual here. I bet we predicted much lower. And this one's probably a negative. We can look at the next page and you can see, here's a picture right here. Can you see that plane? Can you visualize that? I mean, some people are much better at visualizing we're in 2D here, and we're trying to draw a 3D object in 3D space. Can you see that plane here? So this is like this is the plane that minimizes the sum of the squared errors. So for example, that little point has an error, didn't reach the plane, so it has a negative residual, whereas this point has a huge positive residual. So these are the vertical distances. And if you can imagine like a see-through plane, if these little stems poke up through that plane, they have positive residuals. If the heads of them are below it, they have negative residuals. Does that make sense to everybody? Okay, so that's what it looks like. And now let's just look and see if this makes sense. So if you look at the tilt of the plane in the homework direction as we go from 30 to 100, this is the tilt of the plane. This slope is the tilt of that plane. And then, it's the tilt in this direction. And the tilt in this direction, the slope in this direction, as we go from 50 to 100 in exam scores, is steeper. That's what I say at the bottom of the page. See how the slope of the homework is the tilt of the plane as you go from 30 to 100 on the homework axis, and the slope of the exams is the tilt of the plane as you go from 50 to 100 on the exam axis. And notice how the exam tilt is steeper. We can compare these tilts because we're all in the same units. So do you get a picture for how this is working now? All right. Now, if we want to actually look at those three lines that we just did, we can. Like these three lines and these three lines, right? These three lines on page 75. So we can draw them on the plane. I hope it won't confuse you more. Let's start with the ones on page, the three parallel. Here's the three parallel lines or slopes, parallel slopes from page 75. That's the first ones we did. Now, let's see if we can find them. What did we do? We said when your exam was 90, 80, and 70. Well, this is exam 100, 90, 80, 70, 60, and 50. See, it corresponds to these. So what we want is, we'll start, this is the 90. So this line right here, these are the three lines we did on page 75, and let's just get their equations. You can see, you can fit them in here, and then we'll do the other three. Okay, so here we go. All right, so what do we have here? Here we have our exams were what? Right here, we have our exam equals 90. Right here, we have exam equals 80. And right here, we have exam equals 70. All right, and we got this. We said final equals, looking up here, 0.5 0.1641 times the homework, right? And then we said plus 64.376. That was our intercept. Now we're going to get the same slope. You see, so this is everybody who scored an 80 is going to 0.1641 times your homework, but it has a drop, this intercept. And now we only got an intercept of 58.502. We just did this on page 75. And our last one, of course, is 0.1641 times the homework again, plus 52 point, I didn't copy that down, 52.678. All right, so those are those three. And now, similarly, we can get these three. When homework was 70, 80, and 90. Okay, so now homework's going from 30, 40, 50, 60, 70, 80, 90. All right, and then 100. All right, so it's got to be this one. Whoa, it's hard for me to see this. That's 100. So the next one, this one here is 90. This one here has got to be 80. And this one here has got to be 70. All right, so those are the two, those are the ones for your homework equal, this one's the homework equal to 90. This one is homework equal 80. And this one is homework equals 70. And again, we can do the final. So final, final, final. They're going to have the same slope this time of 0.5824 times your exams. And they're all steeper lines, right? And now they're going to have the different intercepts. Okay, so this was the lowest intercept. We got 23.397. The next one was 25. Sorry, all these decimals here, but. And the last one was 26.679. So that's how it all fits in. All right? So these are the three parallel slopes. These are the three parallel lines from page 76. All right, so can we move on, or questions on this? All right, so now you can see where they fit in 3D space. Now, after we do this, I guess it's time to talk about our assumptions. We've talked about assumptions. So what assumptions do we need to do these regressions and to make and to do inference for multiple regression? Well, it's pretty much the same ones we had for simple regression. They're the same ones that we have to have some kind of randomization. You know, if we're going to be computing p-values and doing these significance tests, then we have to have some p-value measures how likely you are to get your observed data if the null was true just by the luck of the draw. So you have to have some luck of the draw, which means some randomization. Either random sampling from a larger population or randomized experiment. All right, and then each predictor variable, like we said before, has to have a linear, not a curvilinear relationship to do a straight line or plane model. And then finally, to use these standard statistical tests, you have to assume that our residuals, our prediction errors, are normally distributed with a mean of 0 and have the same variance, and that they're independent of each other. The same variance, so we don't have bigger error bars with different values, with higher values of x than we do with smaller values of x. All right, and that's another way of saying that is that the errors are independent, identically distributed as normal with a 0 mean and a sigma standard deviation. All right, so they're the same ones that we had for the simple linear models, and we can check these. Let's check them in the context of our example. Were the 107 students chosen from a larger population? Yes, they were. In this in this example, I'm saying at least that they were chosen, we're assuming they were chosen from this large population of 2,000 randomly. So that one checks out. And then the plots for the homework versus final and the exams versus final both did show a linear trend. Let's check it out. We looked at those plots last time. Yeah, they pretty much showed a linear trend. All right, and they were chosen let's assume they were chosen. They actually weren't, but let's assume they were chosen from a larger population for now. We'll talk about later what happens. Basically, people do this all the time, but let's hold off. Let's look at the next one. We can only check these. Okay, the third assumption is what do our residuals look like? Well, we have to first get predictions and then plot the residuals to see what they look like. So we'll do that later once we get our predictions, and we'll see how it holds up. Okay, so we're going to be checking these assumptions throughout. I'm going pretty quickly through them because I want to get to, I want to make sure that you know how to do these significance tests, and I want to get through this chapter. Okay, so what should we do if the assumptions are violated? Okay, the random sampling violated, well, as I said before, that happens a lot. Often people extrapolate to a wider population if the sample seems like it is representative of a wider population, even if it wasn't randomly sampled from one, which is a little iffy, but people do that. So we'll talk about that more, and we can check ways to check how if that's going to lead us to problems or not. And then if the linearity is violated, we're going to try transforming the data, and that's in part 7 to come, and or try nonlinear functions. And then if the errors aren't normal and they don't have equal variance, well, we can do some other techniques. We can use these non-parametric techniques that don't make any assumptions. I love that. That's a lot of fun. That's in part 9. We're going to look at that. We could also do re-randomization and resampling methods. We're going to look at some of those in chapter 22. And again, we can do data transformations, which will come up after spring break. So just a preview of what's to come. Now, all right, is this the last? Okay, so this will be the last chapter, I think, that we'll do today, chapter 20, and then you'll be set to do your homework. And I can give you some time to do it before you leave, because I think that works out well for some people. So let's look at this. All right, so now this is going to look very, very familiar to you because we did this. We've already done this R squared F chi-squared test, even though we didn't have to, for the simple regression. For simple regression, we saw that chi-squared is the square of z-score, and we saw that F is the square of t. I wanted to prepare you for this. So now we're just going to look at it again. All right? And so now, with our regression equation, we find the best fit, the least squared errors, for our particular sample. That's what we're always doing. We fit to our particular sample. But before we go any further, we want to check whether those betas, these that fit our particular sample, how accurately they reflect the betas we'd get if we sampled the entire population. Maybe they're just fitting some accidental features of our random sample. Maybe even our null, that all the betas except the interceptor is equal to 0 would be as good. That would be just predicting, making a prediction where all the final exams are just, the best we could do is just predicting the average final score. And that we really don't do much better than that within typical random jitter. So first, that's called assessing the overall regression effect, testing the overall regression effect. Now that we test more than one slope, we have to test whether any of the slopes in the model are significant. Any of them. That's what we're going to do first. If none of them are, there's not much point in going further. So we're just going to do this overall, testing what's called the strict null, that every one of the slopes is 0. In other words, we don't really have anything in our model here at all. We might as well just predict the average. And then the alternative is at least one of the slopes is not equal to 0. That's the same thing as saying that at least, that's the same thing as testing whether r squared, our multiple correlation coefficient, which is the coefficient between our predicted values and our observed values, whether that's significantly different than 0. So, so remember what significance tests are. They check how far away some random sample landed from what was expected in our null hypothesis, just by random luck. And when we were doing the simple regression, we had the choice of using either a t-test or a f-test, remember? And if we squared the t-test, we got the f. And if we had a large enough sample for the central limit theorem to kick in, a large enough sample, then we'd pretty much do just as well using our old standby, the z-test. And if we squared that, we got the chi-square. So that was chapter 11, so you're in good shape now for this chapter. It's going to be much easier for you because you've already seen it. So with multiple regression, though, we no longer have that choice. We have to use the f or the chi-squared. We cannot go back and use the z or the t. And why? And the idea is because with more than 2 slopes, with 2 or more slopes, we have no way of boiling down the difference we see, the observed difference, into a single signed number. We can't boil the difference between what we observe and what we expect under the null to a single signed difference like we could when we just had 1 slope. Is it different than 0? With 2 or more slopes, we have to look at 2 or more differences and think about it. Some of them are positive, some of them are negative. We can't just take the average of them. What can we do? Instead, we have to square the differences before summing them up to get rid of the signs. And both the chi-square test and the f-test are based on comparing sums of squared differences, called variances. You've seen this many times before. You saw it back in Stat 100 when we had multiple categories and we wanted to see if our observed data fit a model that had multiple categories with the chi-square goodness of fit test or the chi-square independence test when we were comparing 2 samples, each with multiple categories. So we're doing the same thing now here. So if the sample size is large enough, we can use the chi-square test. Otherwise, we use the f-test, and we'll see how they compare. So that's what we're going to be doing for the next 15 minutes, hopefully less. So, breather, questions? Are you good? Are you good? All right. So, again, I like to take one example all the way through, so you see, so it just helps you see what's going on. So what are we saying here? We found this equation that we can predict the finals by this equation, and it's the best fit for our sample. We had n equals 107, and we have now, I'm saying that the r, the multiple correlation coefficient, is 0.6198. That's big. That's really big. This is going to be significant. This is a very big multiple correlation coefficient. And of course, you think it's significant. Don't you think if we test this against the null, what we're saying is, the null says knowing something about somebody's homework or exams tells you nothing about how well they're going to do at the final, which is common sense tells us that's ridiculous, right? So, but pretend we had a less of a correlation here. And the idea is, we want to know whether it fits the whole population better than the null. Okay? This one is pretty obvious, it does, but let's go through the mechanics. So, remember what our chi-square statistic was. It had this part here, the r squared over the 1 minus r squared, that we said was the strength of the model, r squared, over the strength of the error, 1 minus r squared. They sum to 1. We said we can split up the whole variability of the y's into 2 parts, right? So, the strength of the model and the strength of the errors. Now, this little n, where does that come from? Well, you see that it's in the denominator here when we're looking at basically the variability of our errors. And then, of course, when we simplify, it's here in the numerator. And this is very understandable formula, because what it's saying is the bigger your sample size, the bigger your test statistic. And if you recall, the test statistic, here's a chi-square distribution, the bigger it is, it can only be positive. The further out it is, when the null is true, it's about the same, it's going to be, actually it's going to be about the same as its degrees of freedom. So in this case, it would be about 2. And the further it is out here, the more rare it is. Under the null, you'd expect this kind of chi-square distribution. If we get a chi-square statistic that's way out on the tail, that says it's very unlikely to be due to chance. It must be because our null is wrong and our model does make a better prediction than the null. So that's the idea. So big N means bigger test statistic, which means we've got good evidence to reject the null and there's something going on there. So let's compute the chi-squared. So we're just going to do this, our chi-squared. First, what's our r-squared? Okay, so it's 0.6198, and then we'll have to square that, divided by what? 1 minus 0.6198 squared. Okay, so those two have to add up to 1, and that's the core of it. And then the bigger your sample size, the bigger your chi-square statistic. And in this case, we're going to multiply it by 107. And what I got was something huge, way huge, way off the charts here. It was 66.71. That's an enormous chi-square value. All right, so it's huge. As a z-score, it would be obviously huge. Chi-square has different curves for different degrees of freedom, so we have to check it out. And first we have to remember how many degrees of freedom for the chi-square test. Well, remember from last time we said it's the number of parameters, p minus 1. And how many parameters are in the model? Parameters are all the slopes, the two slopes, and the intercept. You count them all as parameters. So this is 3 parameters, okay? Intercept and plus 2 slopes. So I'll write that down. You have the interslope and you have slope 1 and slope 2. So parameters is equal to 3. Now your number of degrees of freedom is your number of parameters minus 1. So the degrees of freedom is the same as the number of slopes, not counting the intercept. All right, so we've got that. We talked about that before, where the parameters include, okay. Remember in simple regression, we had 2 parameters, a slope and an intercept, so we had 1 degree of freedom for the chi-square. And that was the same as the z-squared. So how many degrees of freedom do we have here? I'm just writing it again so you remember it. So that's equal to 3 minus 1, which is equal to 2. That's how many degrees of freedom we have. All right, now under the null, if the null is true, the chi-square statistic follows what's called a chi-square distribution with p minus 1 degrees of freedom. You can write it like that. That little squiggle means distributed as a chi-square, and you put the degrees of freedom down as a subscript. So we can find the p-value by looking at the cutoffs. If you have a chart, like here, looking at the critical values for various p-values on the chi-square table. Remember, the p-value is the probability of getting such a big chi-square if the null was true. So now let's look how to read this chart. Now we have different alpha levels here. This is our standard 5%, written as a decimal. This is significant. We say it's highly significant if it's 1%, and it's super highly significant if it's 0.1%. So there's our p-values right there. Now, 2 degrees of freedom is right here, 2 degrees of freedom, so we go along. And so if we, at the 5% level, all we'd need, let's say that was, for 5%, let's say that was 5.991. So all we'd need, and that's, remember this would be 5%, that whole area. Now, all we need is a value chi-squared bigger than that. And we have a chi-squared. Where's our chi-squared? 66.71. Here's 0. Ours is 66.71. Remember, this goes out forever. Wow. So we have a tiny little speck of significance here. I'd say it's about a p-value of about 0. Should we look it up on our, we can look it up. Let's go to our computer and see what it is. Let's remember 66.71. All right, so let's do that. And just so we can get it online, see if it even shows up. So we have this p-value calculator, right? And we can go to our chi-square distribution, and we have 2 degrees of freedom. And our chi-squared was 66.71, right? And we want to compute a p-value. Whoa! Look at our p-value. It's way off there. That's pretty tiny, isn't it? Huge. It's super tiny. Wow. What if we had one of 2? Because usually, when the null's true, typical values of the chi-square is equal to the degrees of freedom. So let's look at that. So that would be more like 36.79. How about if we do, I think it gets closer and closer. Let's try, like if we had 5 and 5 degrees of freedom. Then it should be more or less like 50%. 41%, I guess, with large, I would thought it would be, what about 100? Look, n doesn't enter in here. It enters into computing, but there's no n value in our degrees of freedom here. I want to see what this is. I thought it would be about closer to 50%. Yeah, we're getting closer to 50%. It's not a symmetrical distribution, so even though it's the mean, it's not the median until you get the mean of the chi-square distribution. It's centered around its degrees of freedom. But this is the p-value, a 50% p-value would put it as the median. And you see how it's not symmetrical? Watch. With 5 degrees of freedom, I just want to show you why. So this could be is the average, but the median is here because it has a long right-hand tail. So when I say it's centered at its degrees of freedom, I mean the average, not the median. But as you get more and more degrees of freedom, it looks like more and more like the normal curve. Does that make sense to everybody? All right. So now let's go back to our, and now we'll look at the F distribution, compute it as an F statistic. We did the chi-square, and now let's go back to the document camera. All right, so let's fill this in, though, just to make sure we know what's going on here. So how big a chi-square do we need to reject it at the 5%? These are called our critical values. We certainly have that. 1% would be here. We need a bigger one. We'd have to get further out on the tail if we only want 1% area. That's 9.21. And if we go even further, if we want, if we go way out to here, that would just be 1% in the right-hand tail. So that's 13.816. So what do we conclude? Well, certainly our chi-squared is huge, so we reject the null. Which is much bigger. So we reject the null, which says the null said all the slopes were 0, the homework and exams. So this, when we reject it, it means at least one of, there's something in the model, at least one, maybe homework, maybe exams, probably, or both, is significant. So we reject the null and conclude either homework, exams, or both slopes are significant. Either one or both. And we'd probably think both of them will be, just from common sense. So do you understand the idea? And then we're going to dive in after this next class, and we're going to see, okay, now we'll look at the individual slopes. And we'll see that then we can do t-tests on them, or z-tests on them. And we'll break it down that way. But before we do that, that's for next time, let's now look at, okay, now let's look at how, we just did a chi-square. Let's look at how, if we did the same thing by an f, and how they compare. So now we're going to do testing the exact same thing using the f-test. And we're going to get very similar results. We'll get a p of about 0. So let's look. The key part of both tests, right here, is this. That's the key part. The strength of our predictions. R-squared measures the correlation between our predictions and our actual values over the strength of our errors. If R-squared, if we had a perfect correlation, we'd have no error. And if we had all errors, so this is the key part of it. Now, that's present here and here. Now let's look at other differences. Okay, so the chi-square curves, they're based on the normal curve, right? And the relation between the chi-squared and the f is very analogous to the relation between the z and the t. In other words, in the limit, as n gets big, they become very much the same. This f gives you a little more precision with smaller samples, but that difference becomes less and less important as your samples grow. And you'll see it's going to be not very much difference. All right, so now let's look at this. I don't know if you remember this, but we went through all of this back in chapter 11. So you might want to just take a glance back there, and we're going to go and we're going to revisit the sums of squares, how that breaks down, and all this stuff. But where was our summary? Was right here, and we saw how we got that, and when we were looking at the slopes, and this is what we got. Now, we had n minus 2, that's n minus p, and we really did have, we have nothing in the denominator here. Now let's look at, so it looks a little different. The chi-square looks exactly the same, but this one looks a little different. Because now, all of a sudden, let's see what it looks like. We have n minus p. Well, that was n minus 2. And it looked a little different because the number of parameters was 2. So 2 minus 1 is 1. So it didn't show up. There was nothing that showed up here. Okay. So let's look at this. Let's first compute the f. All right. So we're computing the f here. And what are we going to get? We're going to get, we still have r, let's look at this, r squared over 1 minus r squared is going to be exactly the same. So of 0.6198 squared over 1 minus 0.6198 squared. Now, what are we going to multiply it by? With the chi-squared, it was 107. But now it's going to be 107 minus the number of parameters. So that'll be 3. So we multiply it by 104 here. Now that, if we did that, they'd be slightly different in the same way they were before. But there's also degrees of freedom. This p minus 1 is the degrees of freedom in our model. This is our degrees of freedom. This is how many, and this is in our errors. But when, of course, we do the algebra, this is in the numerator and that's in the denominator. So we have to divide this by what? P is what? 3 minus 1. So it's 104 over 2. So we're going to get something that's not just slightly less than the chi-square, like we would have, but about half the size of the chi-square, and because we're dividing by 2 down here. So we get 32.44. We'll talk about the significance of that in a minute. Now, how many degrees of freedom in the numerator? Well, that's p minus 1, which is 2. And how many in the denominator? N minus p, which is 104. Now, to find the critical value for f, I'm just showing you this whole table is for p equals alpha equals p equals 5%, right? Because now we have 2 sets of degrees of freedom, so I'd have to give you another whole table for alpha at each significance level. So here's your 2 degrees of freedom in the numerator, and here's your 60. Whoa, we have 104, so it should be right in between there, right? So F, let's write this down, our critical value at 2 degrees of freedom in the numerator and 104 in the denominator is what? Is between 2 values here. Is between what? 3.0718 and 3.15. Let's see what it really is. What? Yes, the non-simplified version, these are associated with the model because the model has 3 parameters, right? It has an intercept and 2 slopes. And once you have on the way to figuring out those, we're using basically the mean to estimate the other ones. The degrees of freedom are the number of parameters minus however many parameters you've already estimated on the way as an intermediate step into getting these slopes. Anyway, to answer your question, this goes with the numerator. And this goes with the denominator, because these are the degrees of freedom for all your errors. You have all those little errors minus your number of parameters. So you have, like, for every single 107 points, you've got a little error attached for it, but then you have to minus the number of parameters, the intermediate steps that went before this, okay? So think, you got a lot of those little residuals, so this goes with this one. Then when you simplify it, of course, this one becomes in the numerator. Is that your question? Yeah. So this is p minus 1, and this is n minus p, and together it's n minus 1. All right, good question. Now you see, let's just say, okay, and now let us get exactly what the p-value is. It's, well, let's just say, okay, so it's between here. I looked online. Okay, I'll just give that to you. Online, the critical value for 2 and 104, and you can look at this later, turns out to be right in between those, and it is 3.084. But do we really need it that carefully? No, because why? RF is astronomically bigger than those. Is equal to what? 32.4. Way bigger than any of those. So we reject the no. And we'll get a p-value. P is approximately 0%. We could do it online, but first, does everybody understand? Does everybody understand? Maybe I should do it quickly online. So since we're here, it's very easy. I was going to give you time to do your homework, but we don't have it. So now I'm going to go to the F distribution. And we have 32.44. 32.44. And our degrees of freedom are what? For the, wait a minute. Look what I did. I screwed that up. I better read it. What do I have to put in there? The degrees of freedom for the numerator is 2. The degrees of freedom for the denominator is 104. And our F value was what? 32.44. Right? Now we're going to compute a p-value, and look how tiny it is. Oh my goodness. It's so tiny. All right? Now, when the null is true, your degrees of freedom for the mean of the F distribution should be 1 when the null is true. So it's so hard to see here, but let's just say we had, I don't know, 10 here and 200 here. And let's say we have a value of 1. And we should get about halfway. So typical values of the F distribution when the null is true are centered around 1. So if you see something 32.44, you know you're going to reject the null big time. Now let's just go back. We have a few more minutes, and I'm sorry to keep you so long, but I want to make sure you understand how to do all the homework. So let's just star this. Okay? So typical values of the F-stat are 1, and typical values of the chi-square is equal to its degrees of freedom. That's what we just said. And, next time I'm going to explain. You should read this on your own, like the difference between the denominators and the numerators. You'll be surprised. And next time we'll start there. We'll start right here. So you can, but I think for now you've had enough, and you should read this on your own, and you have enough to do the homework, and I'll see you on Thursday.